It's a pleasure to be speaking at this meeting. It would have been a greater pleasure had we been able to hold the meeting in person, but obviously that's not happening. So sometime in the future, don't know how long, I hope we can all see each other. What I'm going to do today is use one set of materials or one family of materials to illustrate really several points. One is the complexity of oxide structures in thermodynamics and order disorder. And two is the reason that we can understand it better now than 10 years ago or 30 years ago really relies on a combination of experimental and theoretical techniques. And in that way, I can illustrate high temperature calorimetry using a set of materials essentially on the, based on the fluoride structure. So if I could have the slides. Let's see, what do I need to do here?
There is a button demonstration.
Okay, I guess I need to share screen.
Yeah.
Let me make sure. Got this. Okay, and design slideshow. Okay, I think we're all right here. So let me start by saying that I moved from Davis, California, University of California, Davis, to Arizona State almost a year ago now. It is our summer, so the other experiment in high temperature chemistry and high temperature thermodynamics goes on in my backyard and in the whole part of the state that's at relatively low elevation. And our typical summer weather right now is that the temperature in the middle of the day or in the late afternoon is over 40 degrees centigrade, and the humidity is low, typically around 10%. This is a picture of one of my dogs in my backyard, which essentially is desert landscaped in the sense that it has native plants and things that don't require too much water, whereas the front yard has grass. Let me talk a little bit more about some of the things that we're doing here and some of the reasons that I moved, because not all of you, well, not all of you know me, obviously, but not all of you know that I have moved. So really this is a homecoming for me because I started my faculty career here at Arizona State 50 years ago. And I was on the faculty here for about 16 years, and then Princeton University recruited me. And I was there for 12 years, and then I moved to California, and I was actually in California for 22 years. Well, what caused me at a fairly respectable age to decide to make a move and have a new adventure? In part, it's a confluence of various things, but the most interesting perhaps is what we're calling the Navrotsky Eyring Center for Materials of the Universe. I am leading it right now. Leroy Eyring, of course, was the youngest brother of a big family where Henry Eyring, the statistical mechanics person, was the oldest. And Leroy was a solid state chemist, basically, and really got the solid state chemistry aspects at Arizona State going, from the 1960s to the late 1980s. And those were wonderful years for me as an assistant professor. We had a lot of interactions with solid state chemistry, with solid state physics, with geology. And I visited here about 3-4 years ago, and we started thinking about how we could bring some of that excitement back in the modern context. And what came out of it is the idea of materials of the universe. And the university, at first I thought I was just going to advise them about it, but I ended up really participating very strongly, and I ended up deciding to move in a way to come back home. And indeed, I'm glad to be back in the desert. This was about 2 months ago when the desert was in bloom and the weather was not quite as warm. And the Materials of the Universe initiative essentially has two parts to it. One, the realization of the complexity of planets in our own solar system, that even the outer planets and moons, which we thought initially were just inactive, icy bits of rock, are tremendously active and interesting and have oceans under their surface and all sorts of things. And then the variety of exoplanets that are discovered, thousands of them, really have expanded the thinking about what sort of compositions, what sort of chemistry, what sort of physics. In a sense, the discovery of exoplanets poses the biggest imaginable inverse problem in material science or solid state chemistry. That is, a direct problem or a direct investigation is to say, here is the material, what are its properties? The inverse problem is, here are some properties, what is the material? And of course, at present, in terms of exoplanets, we have limited information. We have something about the size, something about the mass, something about the orbit, maybe something about the outer atmosphere, but certainly in the future, and certainly during the lifetime of people who are now students, we will have much more information. So this question of using chemistry, physics, planetary science constraints, astronomical constraints, to understand what exoplanets might be is terribly interesting. And it requires, because many of these conditions are so extreme that we cannot replicate them in the laboratory, it requires good collaboration between theory and experiment at all levels. The other aspect of materials of the universe is that if we are going to continue doing planetary exploration in our solar system and eventually perhaps beyond it, we need materials that can withstand the difficult and corrosive conditions. For example, the atmosphere of Venus, the low oxygen fugacity conditions on the surface of the planet Mercury, the gaseous planets, all of these at present really, there are no materials that are compatible with those. Similarly, to send spacecraft for a long time, let's say to Mars, with or without people, with or without a manned mission, requires materials that will withstand those conditions, that will protect not just the people, but the instrumentation from radiation in space. So all of this is really a materials problem, and the need for new materials for aerospace is really a pressing need. Even here, the notion of corrosion, for example, thermal barrier coatings on engines that are corroded if they fly through volcanic ash or dusty atmospheres, these are problems that have not been completely solved. And these are problems then that require physical chemistry and especially thermodynamics. That is, thermodynamics tells you what is possible and what is not possible. Kinetics tells you how fast it will occur. But if you don't know what the thermodynamic states are, what the thermodynamic parameters are, you have a very hard time unraveling how reactions might happen. So the Materials of the Universe initiative that we're heading is bringing in new faculty, new capabilities, but especially new collaborations. And I certainly welcome any of you that are interested in it to email me and get some more information. We view this, although the immediate center of this is here, we view this really as part of a global effort. So that basically is what excited me about coming back home to Arizona, and we are reestablishing our thermochemistry laboratory here. So having said that, I'd like to get into the major part of my talk. And the major part of my talk hinges on the fluorite structure. One can think of the mineral fluorite, calcium fluoride, CaF2, or one can think of the high temperature cubic form of zirconia, ZrO2, or one can think of nuclear fuel, uranium oxide, UO2, and all the other tetravalent actinide oxides, or the catalyst materials, cerium oxide, et cetera, and these have a parent structure which is really very simple. You can think of it as a stacking of boxes. That is, the boxes are cubes, and inside every other cube there is a central atom. So this one will have it, this one will have it, that one will have it. And the cubes, of course, are joined by the anions at their corners, and that gives you the stoichiometry AX2, or for oxides, AO2. Well, this is the parent structure, and the structure itself has a number of derivatives and a number of reactions. One of the unique features of the fluoride structure is that it is one of a relatively small class of oxide structures in which the formation of anion vacancies, of oxygen vacancies for the oxides, is really quite favorable and done quite easily. For example, by the substitution of a trivalent ion, let's say yttrium, into the parent fluoride oxide, into zirconia, to form yttria-stabilized zirconia, or YSZ, which is a well-known solid electrolyte material and has many other uses as well. In addition, then, one can have different cations in the central site from the cube. Well, again, once one starts doing these substitutions, the simple random cubic structure in which vacancies are arranged at random and substituents are arranged at random is generally not the most favorable configuration, except perhaps at very high temperature. And a very large family of derivative structures has been discovered and characterized really over the last 50, 75 years. So we have structural families based on the fluorite aristotype, the simple basic structure that ties them together. We have derivative structures which have lower symmetry generally, and essentially more diffraction peaks then because of the lower symmetry. And they are due to distortion and ordering of both cations and anions. There are phase transitions as a function of composition, temperature, and pressure, and one can form a large number of metastable materials, for example, by low temperature synthesis, at which there's simply not enough time to get the most ordered structure, by radiation damage, which I'll be talking about, by grinding or mechanochemistry, and by looking at high temperature where some of the disordering will occur. So it is a rich energy landscape of different structures derived from the basic fluoride aristotype, and one can separate the chemistry perhaps into two categories. One is equilibrium behavior, and the other is non-equilibrium behavior. And the non-equilibrium behavior also includes the behavior of materials when the particles are small, that is nanoscale behavior, either when one has separate little particles or when one has a ceramic of very small particle size. And that in turn also affects the thermodynamics. So what I'm going to do now is give you some examples as we walk through some of these to show you both what is happening and what we've done, we and other people have done to characterize it. So the first sort of structure I want to talk about, and the structure that I will mostly talk about, is the pyrochlore structure, which is a derivative of essentially the fluoride structure. And it is of interest, particularly as a durable material for immobilization of radionuclides and for performance in extreme environments, high temperature, corrosive environments, etc. And it actually occurs also for a number of optoelectronic and mechanical properties. It then basically is a complex structure, and chemical modifications can be made, in particular then in terms of composition, in terms of the numbers of defects and defect clusters, in terms of the ordering of cations, in terms of partial recrystallization of glass. Many glass ceramics of various sorts contain pyrochlore and zirconolite, which is a derivative, further derivative. And the question then of cation mobility and exchange is a wonderful thing. cation mobility, anion mobility are excellent for synthesis. Anion mobility, oxygen conduction is excellent for solid electrolyte properties. But ideally, of course, if one wants a unreactive ceramic that lasts through geologic time, one wants to minimize the motion of atoms. So those are the questions. And then in order to understand these, one needs a combination of techniques. And we have been working on this for, almost 20 years now. We were part of a large center, a National Science Foundation, Science and Technology Center. I'm sorry, that was on high pressure. Then we were a part of a Material Science of Actinides, a Department of Energy Frontier Research Center, which brought together a number of groups to work on many things, including these fluoride pyrochlor transitions. So that work will be highlighted in the next few slides. So the pyrochlors are then a window into high temperature behavior, order, disorder, and thermodynamics. The techniques that we've used to study them in our laboratories center about calorimetry. We have high temperature differential thermal analysis or differential scanning calorimetry, which I will show you some of. It goes up to 2,500 degrees centigrade. We also have our own calorimeters for what we are essentially conventional drop calorimeters, except they are not conventional because they drop small levitated samples. Our main technique is oxide melt solution calorimetry, and we couple all of this with structural studies, and we collaborate with people who do theoretical calculations, particularly density functional theory and molecular dynamics. So let's talk about the structures. The reason for forming these derivatives of the fluorite aristotype is to get better local coordination for different size cations and to accommodate the oxygen vacancies. So the questions that one has, first of all, is, are the positions of the oxygen vacancies and the positions of the cations random, or are they correlated? Secondly, how much order of the cations is there? And if there's a lot of order, then the cation sites become distinct. The ideal pyrochlor structure is a defect structure. It can be, if you write the fluoride structure per 8 oxygens, it would be A408, keeping the 1 cation to 2 anion stoichiometry. If you write the ideal pyrochlor structure, one can write it as A2B207, 1 oxygen vacancy, and 2 different kinds of cations. In reality, the pyrochlors are much more complicated than that, and I do not have time to go into it. And the structure, though still cubic, has these ordered cations. If one compares the structure to the parent fluoride structure, the parent fluoride structure, again, is just this packing of cubes. And if one looks at the pattern of cations and anions, one has a simpler arrangement. And in the fluoride, ideal fluoride structure, you have only 1 type of cation site. In the pyrochlor structure, you have several types of cation sites. Some of these pyrochlors are more distorted than others, and one can even define within the cubic structure the distortion parameter or the pyrochlor-like parameter that says this pyrochlor structure is more like a fluorite, this other pyrochlor structure is more distorted. Let me say something about distortions from a thermodynamic point of view. People often say that a structure is destabilized by distortions. That is not actually true. A structure may be destabilized as a function of composition, but at a given composition, if the distortion occurs, that distortion occurs because it stabilizes the structure under that constraint of composition, temperature, and pressure. So whereas the material may be destabilized relative to some other composition, the equilibrium degree of distortion gives it the maximum stability. And the purpose of the distortion is indeed to do that. And again, then the distortion and the degree of ordering are the major parameters. Again, if we talk about ordering, ordering is a phenomenon which decreases, makes more exothermic the energy of the material, but the price to pay is a loss of configurational entropy. So, as indeed even the last talk alluded to, it's a balance. The equilibrium state at a given temperature for a given composition at a given pressure is one which minimizes the Gibbs free energy of the system, and the degree of disorder essentially at equilibrium reflects that. And in general, then, the degree of disorder increases with increasing temperature simply because the entropy term is bigger. If we go back to, or go to what is right now a very fashionable concept, namely high entropy alloys, high entropy oxides, etc., one has to be very careful. One knows that these are multi-component systems. Sometimes the definition is you need 5 components in roughly equal proportions, but very often these contain a lot of short-range order or even contain ordered phases. So they are not necessarily high entropy. They may be, but it's actually very difficult to find materials where the ions mix completely at random, because the ions are different and they try to maximize their coordination, and generally then there's a lot of partial ordering in them. So the pyrochlor structure is a derivative of the fluoride structure, and I want to talk about disordering in pyrochlors. So low temperature metastable samples can be prepared by aqueous precipitation of various sorts. They are typically fine-grained, nanophase, and quite disordered. High temperature equilibrium samples can be prepared, and they include basically some degree of disorder. The disorder appears to occur gradually with temperature prior to melting. In some cases, there's partial disordering within the pyrochlor, followed by a first order transition to the defect fluoride structure, and I will show you some of that. The non-equilibrium conditions then are essentially low temperature metastable phases, materials produced by grinding, materials produced by radiation damage, and of course composition is a variable. So let's just look at, for example, the stability of, in this particular case, zirconate pyrochlors. What one sees for a large number of rare earth materials is that if one looks at the heat of formation, the enthalpy of formation relative to binary oxides, in general, the larger the cation, that is the early rare earths, have a more exothermic heat of formation than the smaller rare earths. And this is well known for a huge number of compounds, ranging from phosphates to pyrochlors, to many other, to rare earth silicates, etc. And one gets an approximately linear relation with the radius, or for that matter, with the number of F electrons. The zirconate pyrochlors are interesting in that they, as they become less stable, the defect fluorides phase becomes more competitive, and there are actual phase transitions at the end of the rare earth series as a function of temperature. And these transitions are essentially reversible. So those are equilibrium transitions. So how have we studied basically the pyrochlors? We have a combination of structural thermodynamic studies. So X-ray diffraction, particularly using synchrotron X-rays, for example, at the advanced photon source, and there they have laser heating and aerodynamic levitation, which I will come back to, because since some of these disorder transitions are not quenchable, or we don't know to what extent the degree of disorder remains unchanged, it's really desirable to do experiments at high temperature, and we can do experiments up to, oh, about 1700 degrees centigrade, something of that sort. Cooling curves in laser heated aerodynamically levitated samples give us essentially just traditional cooling curves that say here is a phase transition, for example, melting, crystallization, etc. High temperature thermal analysis in sealed crucibles to about 2500, maybe 2700 Kelvin to get transition temperatures and enthalpies. And all of these things then go into thermodynamic modeling by CalFed and related sort of calculations. And all of these things benefit from first principles modeling of the energetics. I should say also that the high temperature X-ray diffraction, of course, gives us lattice parameters, gives us thermal expansion, gives us volume changes on phase transitions and on melting. And those are other things that we can compare with theoretical values and actually generally with rather satisfactory comparisons. So let's talk about aerodynamic levitation and essentially laser processing. One of the difficulties in doing experiments at high temperature is, of course, that everything reacts with everything and often quite fast. So there is no such thing as a totally inert container, and that is a real problem. One of the ways of eliminating the problem is to eliminate the container. And it is now fairly easy using commercial levitators, particularly aerodynamic levitation, which is the easiest, simplest, and cheapest, but also one can do electromagnetic levitation, etc., for at least for things that show high thermal and electrical conductivity. But the aerodynamic levitators nowadays, some of them are commercially available, are really quite usable, and we have one in our laboratory. There is one at the Advanced Photon Source in Argonne National Laboratory. There's one at the Neutron source at Oak Ridge, so that one can levitate small spheres of material, heat them with a laser, and study their properties in situ. This has been done a lot for melts. It's been done for some reason less actually for crystalline materials until recently, but here we focus on crystalline materials. And it is also an excellent way of preparing samples, because then one can very rapidly cool the small bead of material and sometimes get metastable phases that you cannot otherwise get. For example, in the silicates, it's a way of preparing olivine composition, Mg2SiO4 composition, as a glass, which is not otherwise accessible. So let's take a look at the pyrochlor to defect fluoride transition in one of the later rare earth zirconates, gadolinium zirconate pyrochlor. It's a reversible transition. So the in situ patterns show that on heating, you go from the pyrochlor to the defect fluoride, which at least to X-rays looks pretty disordered. And then on cooling, you come back to the pyrochlor. I may say that because the rare earths and titanium, zirconium are relatively heavy atoms compared to oxygen, X-ray diffraction is inherently not very sensitive to what's happening on the oxygen sublattice. Neutron diffraction, neutron scattering is much better for that, and I will come back to that in the discussion of radiation damaged materials. But nonetheless, by doing these in situ high temperature measurements on a series of materials, we have been able to document the thermal expansion, the volume change on phase transition, the reversibility of the transition, and in some cases then as well, the melting of the fluoride structure. So the second thing that we have done is use a commercial calorimeter, slightly modified. It's a Ceteram-Setsys thermogravimetric differential thermal analysis apparatus that normally works to 2400 degrees C, but we've modified it slightly to work to 2500, it needs crucibles. And that's always a problem because we come back to the container problem. And furthermore, differential thermal analysis needs standards. And one of the things that we realized is that there are no good standards above about 2000 degrees centigrade, above the melting of aluminum oxide. It's strange in a way to use the melting of aluminum oxide as a DTA standard, but that's the game we're in. We initially thought that we could use yttrium oxide, which melts at about 2300 degrees as a standard, but there have been, what should I say, the heat of fusion, which we thought we knew, did not make sense in terms of the calorimetry, and that was actually one of the impetus for our drop and catch calorimeter that I will get back to. So anyway, we basically seal our sample in a tungsten crucible and effectively then heat it up in what is in a sense, a normal DTA. This DTA works quite well for looking at phase transitions and for getting enthalpies. Again, at temperatures like this, you know, you don't have the accuracy that you have at room temperature or 500 degrees centigrade, but you do have accuracy in which you can get your enthalpies of transition, typically with reproducibility of 5 to 10%. Temperature measurement is still somewhat problematic. We use a multicolor pyrometer for it. We also use a set of secondary standards. So it's difficult experiments. We are still improving them, but we are able to get reasonable results. So if we go back to the basically pyrochlor to defect fluoride transition in two zirconates, and we correct for the baseline, we basically get quite respectable thermal analysis peaks, quite respectable areas, a little bit of hysteresis. The transition occurs at higher temperature on heating and at lower temperature on cooling, which is quite normal. The areas under the peaks are quite comparable, so opposite in sign, comparable in magnitude, and we get then the enthalpies of the transitions. The thing we can do immediately, having those enthalpies of transition, is, and the temperature of transition, since this is a reversible transition, the thing we can do immediately is get the entropy of transition. And then we can compare that entropy of transition with what one would get if one went from the pyrochlor to a defect fluoride structure in which the oxygen vacancies were completely disordered and the cations were completely disordered. And what we find is that the entropy is observed experimentally is considerably smaller by 50, 60, 70% than the full configurational entropy. So this means probably one or both of two things. One, that there already is some disordering in the pyrochlor structure before the transition, and I will show you that. And two, that even the defect fluoride contains some residual short-range ordering. I'll come back to that when I talk about the radiation damaged materials. At any rate, we get pretty interesting thermochemical data. We have used the high temperature, essentially the high temperature structural studies to create a thermodynamic model for the disordering. And the thermodynamic model essentially takes the cation distributions and oxygen distributions that we've measured from the synchrotron diffraction and fits them to a simple model of the disordering. And this is the simplest possible model that says that on the cation sublattice, the degree of disorder is determined from the site distribution. We assume the cations are at random. Similarly, on the anion lattice. And we then calculate a configurational entropy. For the cation sublattice, it's fairly straightforward for both. For the cation sublattice, it's a simpler formula. For the anion sublattice, just because of the number of anions in the distribution and the fact that one oxygen site does not participate in the disorder. It's a little bit more complicated, but it's sort of straightforward statistical mechanics. We then can use the site distributions that we get to calculate effectively the degree of inversion, the cation disorder and the anion disorder, as a function of temperature. And we have data, good data for 3 systems and not so good data for 2 more, out of which we can then fit, using the simple model that I showed you in the last slide, what the enthalpy of interchange would be. This is analogous to what we did for spinels way back in my thesis work. And basically we get then an enthalpy associated with the cation exchange and enthalpy associated with the anion exchange. And interestingly, the difference between the different compositions, it's a little beyond experimental error, but it's not big. So it seems like the disordering here within the pyrochlor phase follows fairly, follows fairly clear systematics, and perhaps these values can be used to predict other materials as well. So that was an example of an equilibrium phenomenon. That disordering is reversible. It occurs in situ at high temperature. There are other ways to disorder the pyrochlor structure. One is by grinding, mechanochemistry, and the other is by radiation damage. And of course, the radiation damage is interesting from the nuclear waste point of view. So this has been a collaboration essentially between ourselves and Mike Lang's group. Mike is at the University of Tennessee, and he's been collaborating essentially with a group that does irradiation using swift heavy ions in Darmstadt. And he uses the neutron source at Oak Ridge to look at the structures of the radiation damaged materials, so neutron pair distribution functions. He's also measured ionic conductivity at University of Tennessee at Knoxville, and the ionic conductivity follows the disordering and the ordering. We did calorimetry at UC Davis, and Mark Astor did some computations I'm not going to talk about. He's at University of California, Berkeley. And the goal is to then understand the microscopic and structural basis of transformation upon damage and annealing. And the case study we have, the system we studied the most, was dysprosium titanate. So again, if we just say what we did, basically, samples were irradiated in Darmstadt, and then they have to be allowed to cool down somewhat to get rid of short-lived isotopes, and then they're ready to be handled for structural studies, neutron diffraction studies, etc. We do neutron studies at Oak Ridge, and basically this is now a pretty well-established technique. Most of the studies have been done at room temperature, but a few high temperature studies have also been done, which I will not talk about. We do calorimetry using our custom built and now commercially available high temperature Calvé type calorimeters. The commercially available ones are the Alexis, which I believe Sandy Kwan has, and the experiment consists of dropping a small sample, couple milligrams of sample from room temperature into a molten salt solvent, typically a sodium molybdate melt, at a temperature of either 700 or 800 degrees C, and then measuring the enthalpy associated with the process which heats up the sample and dissolves it in the solvent. And the differences in the enthalpies of drop solution then give us the enthalpy difference, give us the enthalpy of whatever transition we're looking at. So what we wanted to do was look at the radiation damaged samples and then look at the samples that were damaged and then annealed at different temperatures for different times. And this led to a number of surprises, particularly when one looked in detail at the neutron pair distribution function. So the idea is that you start off with a pyrochlor structure, you damage it by radiation, and you get a material that is amorphous to X-rays. You can also get a material by grinding, which is a defect fluoride structure. When you anneal the radiation damaged material, you get perhaps a defect fluoride structure. You go back to a pyrochlor and you would like to look at what these different energetics are. This is schematic, and it turns out that the real situation is more complicated. So that's what I'm going to be showing you in the next few slides. So if we do the drop solution calorimetry of the initial undamaged and the irradiated sample, we get a very large difference. That is, the enthalpy of absorbed by the sample to amorphize it is really quite large. If we then do some differential scanning calorimetry on it, and I will show you this conventional DSC up to 1,000 degrees, we get what looks like a pyrochlor phase to laboratory X-ray, but in fact we don't get back all of the energy that we put into the sample. We get back about half of it, which means that there is still some sort of damage, some sort of disorder that occurs. And this is completely in keeping with the structural studies. So we did differential scanning calorimetry on the damaged sample. And we found that essentially in a normal DSC scan, we get an exothermic crystallization peak at about 800 degrees C. But that peak has a long tail going up to 1200 degrees C or so. We would have liked to do more studies, but again, even with the Darmstadt irradiation of samples, the amount of sample one has is limited, so we could not immediately go back to this. But nonetheless, this peak accounts for about 1/3 of the total damage energy in the sample. This whole peak maybe accounts for about half. So clearly then, the sample, after it's been heated to 1,000 degrees or even 1,200 degrees C, although to laboratory X-ray it looks like pyrochlor, something else is basically going on in the material. And we don't know, if we were to anneal it for months, whether it would go all the way back. Now, the exciting part comes from the neutron studies. The neutron studies are sensitive to the oxygen positions as well as to the cation positions. And if one does neutron studies, one finds that in addition to the pyrochlor peaks, or in addition to the lack of peaks in something that we called an amorphous sample, there is some short-range order. There is a significant amount of short-range order, and I don't think I've got a slide on that. No, I don't. But basically what has been found by Lang's group, and they're continuing to refine the data, is that you get a formation of domains, nanoscale, perhaps 10 nanometers, not more than 50 nanometers, more or less randomly distributed within either the amorphous structure or the pyrochlor structure. And those domains are built on a motif that is another structure derived from fluorite. It's something called the Weberite structure. I'm not going to get into the structural chemistry in detail, but the Weberite structure in a way is an intermediate in terms of disordering from the pyrochlor, which the ideal pyrochlor is fully ordered. The defect fluorite, the ideal defect fluorite, is fully disordered. The Weberite has a large number of crystallographic sites, some of which intrinsically contain disorder. The Weberite structure occurs in a number of other materials as well, and I'll come back to that. So what we found then in combining the calorimetry, the neutron diffraction, and also some first principles calculation is that our situation is much more complicated. If we irradiate the sample, We put in a lot of energy, we get a high energy state. If we then anneal the sample to 800 or 1200 degrees C, we get back something on the order of half the energy, but we have a structure which shows a lot of pyrochlore structure in the long range, but in the short range, it shows these Weberite domains. And in fact, the material that is amorphous to X-rays also shows these Weberite-like domains, and they persist for a very long time. And in fact, then, for them to go back, for the sample to go back to the initial stage, to the initial pyrochlore state, we don't know how long that would take. We have not done experiments that would be a month longer, a year longer, something like that. If one grinds the sample, and this is a separate set of studies that we've done, that produces a defect fluoride structure that has about the same energetics as this annealed radiation damaged material, but it is in fact quite different. The annealed radiation damaged material is a pyrochlore structure with domains of Weberite. This is a defect fluoride structure, and it's not clear whether it has domains or not. We've looked at a number of other zirconates, titanates, etc. The overall picture is the same, although the actual values that we get are different. So, conclusions for radiation damage. The enthalpy of amorphization is about twice that of disordering the pyrochlore to a fluoride-like phase. That is, if one compares the radiation-damaged quasi-amorphous material to the mechanically damaged defect fluoride material. Annealing the amorphous phase to 1200 degrees shows crystallization and ordering, but the pyrochlore is not completely ordered, and only half of the stored energy is released, and therefore this is important for nuclear waste forms, that one doesn't get back to the most stable material. Weberite short to mid-range order plays a tremendous role in both the structure and the energetics, also in things like the mechanical properties and the ionic conductivity. As long as the material is partly disordered, it has higher ionic conductivity than the parent pyrochlore. Different compositions behave similarly, but with different parameters. Let me talk a little bit more about the Weberite structure. We've begun to look at a number of Weberites and look at their energetics. And what we found is that, first of all, the Weberite structure is even more widespread in materials than the pyrochlore. It is a structure of choice in a number of ternary fluorides. It occurs, in fact, it's one of the sodium magnesium fluoride Weberite is the actual mineral. It interestingly can occur as a mixed organic inorganic material with some organic large ions, and it occurs in a number of oxides. And now we're looking at, can one transform in any case Weberite to pyrochlore to defect fluoride and vice versa. In general, the Weberites have a different composition from the pyrochlores, although the overall stoichiometry of A2B2 of let's say 4 cations and 7 anions is maintained roughly. And we are continuing to look at this. To give you one more example, here we go. No, we did. I didn't. We're continuing to look at this and to think about short range order in the defect fluoride, short range order in the Weberite, short range order in the pyrochlore, intergrowths and transformations. There's a lot of work to be done. I did not talk about our drop and catch calorimetry because we have not actually gotten data for pyrochlores in it, but we've gotten data for rare earth oxides, aluminum oxide, etc. So what we do basically is levitate a small sphere, typically a few millimeters in diameter and something under 100 milligrams in weight, of an appropriate material, an oxide, and then have it laser heated, measure the temperature, drop it into a calorimeter at room temperature. So this is like a conventional drop calorimeter, hot sample to cold calorimeter, and measure the energetics. And here again, we just show our little glowing sphere. We show our calorimetric peak, which of course is quite respectable. That's at room temperature. And we show for aluminum oxide and for yttrium oxide that we definitely get the heat content as a function of temperature, a phase transition, in this case melting, and then the melt. We're not quite confident about relating these slopes to a heat capacity simply because we don't have as good a control on temperature as we would like. That's something we're going to be working on. We now have a good enthalpy of fusion of yttrium oxide, which we can then use, for example, as the calibrant in the DSC. And initially, in fact, building this apparatus, this drop and catch calorimeter, one of our purposes was to measure heats of fusion of oxides that we could then use as DSC standards in the 2000 to perhaps 3000 degrees C range, and we have succeeded in that. I would like to close with a comment that we have a Thermodynamics consortium that is free to join, for people to join, and several of you have joined already. And the idea is to just be a clearinghouse and a discussion group and so forth on all things thermodynamic, conferences, papers, etc. And we have over 200 members now from all over the world. And again, contact me if you want more information. So, to conclude, I want to thank you for listening. I hope that all this thermodynamics hasn't put you to have a nice nap in the sun as my dogs are doing. And again, I will be glad to entertain questions.
A second. Thank you for your talk, Alexandra. Questions? Okay, while our colleagues are looking for there is a question. Dear Prof from Irina Ospenska, are you going to ask yourself? No, okay, I will read. Dear Professor, thank you for the excellent presentation and the opportunity to participate in our online conference. I sent from Russia with love. And I have one question from me. You have shown the DTA for 2500. How did you reach these temperatures? Have you changed the furnace?
No, it was in fact a software problem.
Oh,
they had a limit of 2400 just to be on the safe side. They said, well, we can probably run it to 2500. It might shorten the life of the furnace and so on. But they went in there and they fixed the software for us.
Okay, thank you.
Can one go even higher? I don't know. We have, of course, our sample holders and our thermocouple. I mean, the main limitation actually is thermocouple drift. We use tungsten rhenium thermocouples because, of course, with the tungsten crucibles and so on, we have to have, we have to have reducing conditions, and anyway, we're above the platinum alloy range, etc. So I think, thermocouples are a problem, and that they age, and at higher temperature, they age faster. The detector ages as well, so one needs to try to do calibrations, sometimes with an internal standard. If you can put in an internal standard that doesn't react with either your sample or the container. But it was not actually a calorimeter limitation.
Okay, thank you. There is two questions, one from Alex Fish. Alex?
Yeah, thank you. Thank you for the great talk. I have a question about the tungsten crucibles. You said that you have protective gas outside, so there won't be any reaction outside of the crucible. But inside the crucible, you have an oxide, which at higher temperature may release some oxygen and react with the tungsten and make tungsten oxygen gas species that may then go into your crucible. So how do you check if there any interaction takes place in the crucible? Because sometimes you can see it, probably your sample goes out, but you still have some tungsten inside the sample.
Yeah, I mean, most of the materials we've run are, stable oxidation states. So they're probably not going to give up much oxygen, though we did see some very strange things in some of the heats of fusion that make us, but this was in a different set of experiments. We always analyze the sample after we get it out. And in worst case scenarios, we see some reaction, we see some secondary phases. I would say that the main way to minimize reactions is to keep the reaction time short. But you never eliminate it. Again, in cases where where you get reproducible results, and particularly if you can get reproducible results on heating and on cooling, certainly another way when you're doing, if you're doing melting reactions in the calorimeter, then obviously if you've got reactions with the crucible, you get into a multi-component system and your melting point starts changing, and that's that if you can separate it from thermocouple drift is another way of saying how much reaction do you have.
Can I ask a second question?
Yes, please.
It's about the drop and catch calorimeter. How do you calibrate the temperature?
So we're calibrating the temperature of the levitated droplet by a spectropyrometer. The difficulty still is that that's a surface temperature. So again, it's a little, what's the temperature inside? The sphere isn't perfectly spherical. Sometimes these little spheres have little cavities in them. So we've also tried to basically come back to saying, let's see from our other experiments if we have some materials with known melting points. We haven't tried to calibrate versus laser power because that's not, so I would because that's not as reproducible as we'd like. So I would say that when we're near the melting point of something that we know, then our accuracy is, plus or minus 10, 15 degrees. When we're not, and when we're at the higher temperatures above 2000 centigrade, I would say we might have as much as 100-degree uncertainty. It's not going to matter that much in terms of our heats of fusion that we measure because it's that different, because the calorimetry is done at room temperature. So the sample drops in, and as long as we have the same heat loss, et cetera, which is another set of discussions, but we could get the alumina data, which were measured before, we could get it quite accurately so that change in the heat content curve is accurate. Because we're still working on better ways of calibrating the temperature, that's why we have not yet gotten heat capacities out of the measurements. So, it looks like the slope of the enthalpy versus temperature curve is a little bit bigger for the melt than for the solid, which is what one would expect. And if one is brave, one can take that slope and get a heat capacity, but I'm not yet quite brave enough.
Okay. And do you have an idea how much heat you lose during the fall?
Since we've calibrated using materials with known heat contents, as long as that heat you lose is a function of temperature, it's a function of material. The distance you drop is very, very small. So for example, since you have the melting point and you get the heat of fusion, you get the heat of fusion of something like alumina, which is known, I can't give an absolute value on it, but I can say with reasonable confidence that it's essentially a constant factor for a given set of conditions, and therefore it sort of comes out in the calibration.
Okay, thank you.
Thank you. And Igor Abrikosov?
Yeah. I will reformulate my written question in a little bit different way. I'm a theoretician, and my question is, when I do calculate mixing or enthalpy at high temperature, at what level of disagreement with experiment I say that we are off, or we are still in agreement? So is it possible to estimate the experimental accuracy in these terms?
To estimate what? I'm sorry. What was that?
Estimate the accuracy or the uncertainty of measurements of enthalpy at high temperature. So is it possible to estimate in the sense for me to answer?
Yeah, it might be. I mean, what we get basically, and this is work that we've done mostly with that on van der Walle's group at Brown, they get when they do initial DFT and then molecular dynamics and take everything to high temperature, which is, an amazing tour de force, basically. They get heats of fusion and melting points that are, that, what should I say, are typically within 10, 20 degrees of what we measure. Now, is that accident? Is that real? And of course, the other thing that is very difficult to say is, what are the error bars on the calculations? And those are, there's all the theorists I talk to say there is no real straightforward way of answering that. So I'm not sure, that I would use that. I'm not sure that I would use the calculations to calibrate the temperatures or the experimental temperatures to calibrate the calculations. I would say when both of them are, within a few tens of degrees of each other, and what's rather amazing is the heats of fusion are also within 10% of each other. Well, we're either doing things right or it's an accident. But the more systems you do, the more confidence you have. So that's kind of a little bit of a vague answer, but I would not feel confident saying that one thing can be used to calibrate another, because probably the uncertainties are sort of comparable.
Thank you.
Thank you. More questions? No. I don't see anything appearing in chat. Okay. If that is not the case, we should thanks Alex once more for joining us and giving such a fantastic talk. It's always a pleasure to listen to you.
And I thank you for the opportunity. And, I look forward to any other discussions by email or individual Zoom calls or something. I think one thing that the pandemic has taught me is the distance doesn't matter, that one can have good interactions with people. And I have been having more interactions with people internationally and with old friends and colleagues and so on, because we have a little bit more time. And indeed, I think a lot of us are doing a lot more sort of, deeper, more relaxed thinking as we're sitting at home. So we may see the benefits of some of this over the next several years.
Thank you.